Last time we talked about inequality constraints, and then we did a whole bunch of stuff about interior point methods, right? And we ended up at the end yesterday or 2 days ago talking about QPs, right? Quadratic programs. And we ended up finishing up with a little toy QP solver interior point method, right? And that's in fact a question on your homework. So we're going to basically ask you to slightly extend the version from class. Essentially just put together the equality and inequality constraints into one solver. It's super easy. All you do is put both things into one stacked up set of KKT conditions. So you'll end up with a Lagrange multiplier for the equalities and a Lagrange multiplier for the inequalities and some log barrier stuff, and you'll just stack it all together and let it rip. So it's just combining the two things, which is on the homework. Should be relatively straightforward. Shouldn't be too much of a stretch. Okay, so that's what we did last time. Any question about any of that stuff? Okay, so today we have two final little optimization sort of demons to slay, if you will. So we got to talk about, basically, we're going to revisit both regularization and line searches, specifically for constrained optimization, right? So we did both of those things in the unconstrained setting before, where we didn't have to worry about constraints, and there's some slight tweaks that you have to make to deal with the constraint stuff. So that's first. So regularization and line search. So I'll be real quick, do that. And then we're basically done with our optimization crash course. So you'll officially be sort of equipped with some tools and enough to be dangerous. And then we're going to have a little palette cleanser today because we just did this whole crash course thing the last few weeks. So we're actually going to start getting into control today. So first, as a little, kind of palette cleanser, we'll do a little control history thing for fun. And then hopefully we'll start kind of getting into what we'll call it deterministic optimal control at the end today, hopefully, time allowing. Okay, cool. Any question about anything? Everyone feeling good? Okay, so first thing I want to do is take us back to where we ended up last time, specifically our little QP solver. So let's grab that. My computer's hopefully going to cooperate today. All right, everyone see this okay? So this is exactly where we're at last time. I'm just going to run us back to where we were. Blah, blah, blah. Everybody hopefully remembers this thing. So this is, kind of the relaxed barrier stuff, Newton solver. And then what I'm going to do real quick is just plot. We're going to plot kind of, what's going on here. And so this is where we're starting out over here. That's all good. But specifically what I want to do is inside the Newton solver, we're, solving this linear system. And this is the matrix we're kind of inverting in our linear system, right? And we remember from our previous discussions on kind of Newton's methods, a root finding method. It doesn't really care if it's a max or a min. It's just going to go to the nearest stationary point where the gradient's 0. We've had that whole conversation. And we talked about specifically in that context, right? If you want to make sure you go downhill on the cost to get to a minimizer rather than uphill getting to a maximizer, what do? We regularize specifically because we want this Hessian thing to be positive definite, right? That was the story before in the unconstrained setting. So let's take a look at this guy. So I'm just going to, use for diff on this. What's going on with our eigenvalues? They're not all positive. So this is not a positive definite matrix. Okay, I'm over here, whatever. Let's see what happens, right? So we can go ahead and solve this thing, right? Take some steps, whatever. And I'll start us out at a pretty aggressively cranked barrier parameter. We're basically right on. Let's take a look at it again. We got a negative eigenvalue in there, right? So I can go all the way, right? I can crank this thing all the way to totally converged on here and pretty much, and at an optimum, this thing has a negative eigenvalue. What's going on? Anyone have any thoughts on this? Why is this still working? What's happening? Well, first of all, what does it mean if I have a negative eigenvalue in there? So I have positive and negative eigenvalues from a just kind of landscape shape of the, situation, what does this correspond to? It's not a minimum. It's not a maximum. What is it? It's a saddle point, right? So this is a saddle point. And anyone have any thoughts on why that's a saddle point or what's going on? Or is this okay? Clearly it's okay in the sense we're getting the answer. And it's doing the right thing. So what's up with that? Why is this a saddle point and not a minimizer? Anybody got any ideas? That's kind of true. Yeah, I mean, it does, right? So there's something about the constraints that's, kind of at play here, right? Because in the unconstrained setting, it's a quadratic bowl. And I know what the eigenvalues are because I wrote them down, right? So it's a diagonal matrix and they're positive. So something about the constraint here is making this a saddle point. And I guess the deeper thing is that that's actually the right thing. So this is kind of funky. Has anyone seen this before? No, it's more weird and subtle and interesting than that. Okay, so good. Nobody knows what's up right now. So I get to show you something new today. Okay, cool. So that's a thing that you should know about. And now I'm going to tell you why that's the thing that it should be. Okay, so now we're going to talk about, I guess, this is actually sort of deep and sort of cool. So we're going to kind of get into what's called duality in optimization. And it's deep and cool and there's a bunch of theory stuff, but it's actually got a really practical thing that we're going to, kind of about the regularization story that shows up on your homework also, which is why we're doing it. Yeah. Because if we didn't have them done the bowl, it's just a bowl, right? So the bowl, the global minimizer there at the bottom of the bowl, the whole landscape, right? The cost function itself is convex, strongly convex, positive eigenvalues everywhere, right? So it has something to do with the constraints. Nothing to do with linearizing. Nope. All right, we're getting into it. It's gonna be fun. Okay, so we're gonna start with our prototypical nice, easy. We're going to start with the equality case because it's easier to explain a little bit, but it's not too big of a leap. We're going to do both. So if I have this guy, which is, again, we've been talking about now for a couple of weeks. So minimizing, and we have this C of X equals 0. And I mean, for this purposes, it can be convex, not convex, kind of doesn't matter. But we'll assume life is good and, it's convex and there's no weirdness associated with either of these functions for now. Okay, so, and this is actually closely related to the log barrier story. So this is all kind of, which is why we're doing it now and not before. Okay, so we could theoretically take this thing. I remember we talked about penalty methods, how you could stick a big penalty on that constraint, stuff it in the objective, and how in some sense the log barrier is kind of like an infinite, super stiff penalty. So let's think about that for a second and really kind of, if you could make up the perfect penalty, forgetting about numerics and smoothness and everything, what would be the perfect best penalty, the exact penalty for this thing? It would basically be something where, there's no penalty when the constraint's satisfied, and the penalty jumps to infinity as soon as you violate, right? That would be kind of like an exact penalty. So let's write that thing down. So in theory, we could do this. Obviously, we can't do it in real life because numerics will blow up and be terrible. But theoretically, we do something like this, and we're going to call this a P infinity for infinite penalty of C of X. And we're going to define this thing such that this P infinity of X is 0 when the constraint is 0, when it's satisfied, and then infinity plus infinity otherwise. So if we're violating the constraint, this thing is just going to blow up to infinity instantly. Okay, so this is obviously terrible. I can't do this in real life, but I might want to do this, right? This is kind of the ideal thing. And in some sense, right, the log barrier is approximating this kind of thing, right, in a smooth way. Okay, so it turns out, though, so this is practically terrible. But we can get the same thing. And this is also very closely related to the log barrier story. So log barrier has a, it's smooth version of this, but it still blows up in a way that seems terrible. How do we fix the log barrier? What trick did we play to make that actually numerically work out? This dummy slack variable, which turned out to be closely related to the Lagrange multiplier, right? So the trick is this so-called Primal-Dual trick. We introduce a new dummy variable and do this little kind of trick, and all of a sudden now the Primal-Dual problem is better, right? So we're going to do the same trick here. It turns out that's like a that Primal-Dual trick of like introducing a dummy variable when you have bad stuff is pervasive. It shows up in a lot of contexts. It's like something to, kind of try to wrap your head around. But we can get the same kind of the same effect here by solving the following thing. So if I have my min over x, but now I'm going to introduce a new dual variable, and I'm just write this down and then we'll talk through it. So we've got our f of x we're trying to minimize, and then we're going to introduce this Lagrange multiplier term, lambda transpose c of x. And the idea here is I'm minimizing x in this outer problem, and then the inner problem, I'm maximizing this thing with respect to lambda. So the idea is if c is non-zero at all, that inner max over lambda will blow this up to infinity, right? If c is 0, then it can't do anything. So the penalty goes away. So this minimax, so-called minimax problem, right? Outer min, inner max, this is exactly mathematically equivalent to the infinite penalty. Does everyone see that? So I've turned this infinitely bad penalty thing into this actually well-posed minimax problem that I maybe can actually solve, right? And this should look very familiar, right? The thing in there is what? It's the Lagrangian, right? So that thing on the inside is the Lagrangian. Does everyone see this? So, so let's write that in words. So whenever c of x is not 0, the inner problem blows up. Okay, and then we can actually do the exact same thing in the inequality case. So I'll write that down. It's slightly tweaked, but it's tweaked in exactly the way you would expect, and it is consistent with everything else we've been doing. So for inequalities, where we've got min over x, f of x, subject to c of x positive, we're going to take this. We're going to do same trick. Min over x, f of x, and then here slightly different, right? So we're gonna now have like a one-sided infinite penalty. So we're gonna call that p infinity minus, because it blows up to infinity when the argument is negative. C of x, blah blah blah, and then this thing is defined how you would expect. It is 0 when the constraint's satisfied, so when c of x is non-negative, and then it's infinity when c of x is violating the constraint, so when it's negative. Cool. So I can do the exact same trick. I can take this thing and reformulate it just like we did before as a minimax problem. So min over x with the one change that now, what has to change? Well, kind of two things. But based on what we've done so far, what's going to have to be different about the lambda in this case? Lambda has to be positive, right? Just like the KKTs that we've been doing. And this should be kind of obvious once you see it. So now the inner max is actually a constrained maximization problem where lambda has to be positive. Otherwise, this is the same. What sign do we have on the Lagrange multiplier term? It's got a minus sign on it, just like everything else we've been doing. And this should hopefully clear up any confusion you had about that. So now think about it. Okay, so whenever c of x in this context is positive, so what happens to the inner max? What's the best it can do? Because remember, there's a minus sign and lambda's got to be positive too, right? So the best it can do is zero that term out. So I guess I'll just write it in math. Maybe I'll just go like this. So basically you see that, and then if it's negative, I can drive lambda to infinity, blow that term up. So it's the same exact sort of like intuition. with a change where it's just got some sign stuff on it. Okay, so everyone clear on this stuff? So we can do this infinite penalty trick, and it turns out this is like very, very closely related to the Primal-Dual kind of trick, and Lagrange multipliers are all kind of tied up in this idea. So now the question is, when I'm solving my Newton thing on a Primal-Dual problem where I've got both x and lambda, what kind of optimum am I actually finding? A saddle point. Why? Because I'm minimizing with respect to x, so that I want that in x, it needs to be convex locally. It's got to be a bowl, but I'm maximizing with respect to lambda. So that's the opposite. So in lambda, if you imagine if it's a problem with just a scalar x and a scalar lambda, if I imagine that optimum in x space, it's got to look like this, and in lambda space, it's got to look like this, right? It's got to be a maximum. So that's kind of a key idea here. And it turns out whenever we solve a Primal-Dual problem over both an x and a lambda, we're actually finding a saddle point. It's a saddle where it's got to be positive definite in the x directions and negative definite in the lambda directions. And so specifically, it's actually a very specific kind of saddle where we actually know exactly the number of positive and negative eigenvalues that I should have in that Hessian thing, right? I've got to have dimension x positive eigenvalues, and I have to have dimension lambda negative eigenvalues. Does that make sense? Okay, so now how do we regularize this thing if I need to regularize? So I know exactly how many of each type, and in the upper left block that corresponds to the x's, just like before, I'm going to put a positive regularizer, but in the lower right block that corresponds to the lambdas, I'm going to put a negative regularizer. Does that make sense to everybody? And that's how I force it to be the right kind of saddle. And basically, it's forcing gradient descent. It's forcing descent on the x's and ascent on the lambdas. You can actually do very similar things with first order methods. So there's a Primal-Dual sort of gradient methods, same deal. You actually you basically go in the negative gradient direction with respect to the x's and the positive gradient direction with respect to the lambdas to kind of find a saddle. Okay, any questions on that? Let's write that down. So I have interpretation here is these KKT conditions that we've been looking at define a saddle point in sort of x lambda. And so practically speaking, KKT system should have kind of a dimension of x positive eigenvalues and dimension lambda negative eigenvalues. At an optimum, right? That's how we know we found a saddle. So that's the second order sufficiency thing in this case. Yeah, what's up?
In the way that we represent a minimax, which like player gets to go first?
That's a good question. So what you just described there, or that question you asked, right, is actually so you're thinking game theory, right? And that is a specific kind of game called a Stackelberg game, where it's a two-player game and there's an ordering. There's other more general kinds of games, in particular Nash games, Nash equilibria, where there's sort of a notion of symmetry between the players and there's no notion of like, you know, who's first and who's second. In fact, you can have n-player games, right? So this is kind of more analogous to the Nash equilibrium.
Doesn't matter which point the order we write it.
It does. This is actually fun and subtle. Yeah, so here's what's up. Okay, so this is an exact reformulation of that infinite penalty thing, right? It turns out if I flip the order of the min and the max, that's called the dual problem.
Right.
And yeah, so you know some of this stuff. Okay, so what can you tell me about that dual problem? When is that going to have a solution? Blah, blah, blah. What do you know about that?
Strong duality evolves, then will be the same.
Yeah.
Weak duality, then like.
Okay, so for the rest of the room, this is a cool thing that we'll maybe should talk about. So if I flip the order of the min and the max, it turns out if the problem is strongly convex, I'll get the same answer. And if it's not strongly convex, in general, I won't get the same answer. And the difference between those two is called the duality gap. So the gap between, so the original problem and this dual problem where I flip the order of them. So I do max on the outside, min on the inside. The difference between those two is called duality gap. And there's all kinds of nice theory about this. The cool thing about flipping it is the flipped problem is always concave, i.e. negative convex in some sense. So that means you can always solve the dual. And because of that, because you can always solve it and has this nice concavity property, you can use the dual to get a like lower bound on the original problem, which can tell you something about the original problem. So that's useful. There's also, by the way, so we talked about convexity, and if it's strongly convex, you can flip and get the same answer. Sometimes that's actually useful. Sometimes the dual problem is easier to solve than the original one. The other kind of fun fact is there are actually random non-convex problems with zero duality gap. These are kind of like rare, like rare little nuggets kind of lurking out there in the wild, but there's a few known ones. And in those cases, you can solve the dual, which is concave, i.e. convex problem, and get the exact solution to this original non-convex problem, which is kind of wild. And there's a few instances of that. So I don't know. Life's crazy, but yeah, thanks for asking. That's cool stuff. Any questions about any of that? This is sort of extra fun. If you care about this, I can point you to some stuff, but this is sort of not, it's a little beyond what we kind of need for the class. Yeah.
The condition is, the constraint is flipped. Like, the problem would be fx plus lambda.
So if you flip everything around, like what that would, so if you wanted C to be negative rather than positive, a bunch of stuff flips, yeah. So you could either flip the sign in front of the lambda transpose C, or you could flip the sign on the multiplier, and those would be equivalent things. There's many options there. You just have to make sure you do the right combination of options. The other thing you can do is flip the outer problem to be a max, right? And that flips all the signs. So there's like sort of a bunch of ways, all of which are completely equivalent. You just have to make sure you get the signs right. And that comes back, still a mini-max problem in principle, but yeah, like the gist is you need that multiplier term to act like a penalty. It needs to make the cost worse when you're violating the constraint. That's the whole thing. So just stare at it and make sure it gets worse when C is violating. That's kind of the whole game. So that's how you can figure out the signs on everything at the end of the day. Yeah.
If the constraints are satisfied,
I mean, no, like it'll just kind of.
P of x is greater than or equal to 0.
Yeah, so, but I have this constraint, right? It's lambda's got to be positive. So if C is satisfying the constraints, and I have, i.e. it's positive, and lambda's got to be positive, that's making the cost better. So it's not penalizing anything. Does that make sense?
It's making it better, right? So
Yeah. So yeah, it's a little subtle. It turns out like there's sort of a place where they balance out, basically. Which is this kind of saddle idea. So that's, yeah, I don't know, maybe there's some pictures that we can draw here. But yeah, maybe we can talk about this offline. Okay, everybody cool? Good. Yeah.
So the negative eigenvalues have to do with the gradients.
No, it has to do with like the kind of the so it does. Maybe let me write this down and then it might be a little bit more clear. So we've got this situation. So, oh yeah, this condition on like the signs of the eigenvalues, this is called being quasi-definite. That's good to know about. So KKT systems, because these things show up all the time, they're called quasi-definite linear systems, and they have specific sort of numbers and combinations of eigenvalues. And when we want to regularize this thing, I want to do something like this. And I got my, say, delta x, delta lambda equals minus grad x of Lagrangian and minus c of x. And here, right, the beta is our regularizer. This guy's got to be positive. And sort of just to kind of emphasize this a little bit, right, this guy's positive, this guy's negative. Okay, so that's kind of what this should look like. Okay, so yeah, there was a question over here about this. So what these signs are corresponding to is really like the curvature around the optimum. So specifically, right, this is basically the Hessian of the Lagrangian, right, in both x and lambda. And based on this minimax story, right, it's got to be a minimum with respect to x and a maximum with respect to lambda. So that just literally corresponds to the eigenvalues are positive, it's convex, and it's a local minimum if I have grad equals 0, right? And if the eigenvalues are negative, it's concave. And if the gradient's 0, I'm at a local maximum. Does that make sense? Maybe, maybe not. All right, come talk to me after. So let's do this. So I want to then revisit, we kind of looked at this. This is the problem that we've looked at a whole bunch where we've got a kind of nice bowl, and then we have a non-linear constraint. We have this like quadratic equality constraint where I have to be on the yellow curve, right? And it turned out if I started kind of in this spot and took regular Newton steps, it looks like I'm making progress, but then I got into this weird situation where I went backwards and kind of got stuck and never made it to the optimum. So let's try to get that to happen again. Yeah, so I think we're kind of getting there. Yeah, so we ended up like kind of settling over here somewhere. And if I kind of keep stepping, I end up converging not only to a like not only to not, like the optimum I want, but I actually converge to an infeasible point too, right? The constraint violation is non-zero. I'm not even on the constraint. So this is very weird and bad. Okay, so what do we suspect is happening here in line with like our previous kind of, talks about regularization? So before we went uphill instead of downhill, and that was because we had the wrong sign on the eigenvalues. So similarly here, we're trying to find a saddle point with a certain kind of combination of eigenvalues. And we're in a situation very much like that here, where we're picking up wrong signs on things. Let me see if this is, so we should have 2 and 1 here. It's in the right place. And actually see what I'm doing over here, which is very annoying. So, okay. This gets stuck. We're going to do the regularizer the way we talked about. So we're going to put the positive beta on the top left, the negative beta on the bottom right. We're going to check the number of eigenvalues and make sure that we've got kind of dimension x positive ones and dimension lambda negative ones. This is, again, like a very inefficient way to do this, where we're computing a full eigendecomposition. Like we said before, there's cheaper, better ways, but this works. And we're going to go ahead and do the exact same thing, start in the same spot. And now we're going to take some Newton steps and see what happens. Blah, blah, blah. Kind of shot way over here. So maybe this is bad from a overshoot perspective, but we made it around the corner now, and we're going to end up converging to where we want. Cool. Regularization saves the day. So it's basically just making sure you're taking the right direction steps. And in the other case, it was they stepped in the wrong direction because of that. Cool. Any questions about this? Cool. So now we know how to regularize constraint problems. And we know about this kind of quasi-definite situation where what we're actually doing when we solve a primal-dual problem with both x's and multipliers, we're actually doing a mini-max thing. Cool. Okay. Yeah. That's right. It does not. Well, and specifically, so this, we're going to get into this right now. I still have this overshoot problem, right? Like I still kind of shot way off the constraint. It maybe got worse, right? So I still need a line search, which is exactly what we're going to talk about now. This has no line search, right? So overshoot problem is still a thing. And now we got to talk about how to do line searches on these kind of, constrained problems. So let's do that, unless anyone has any.
It won't be decreasing.
Well, what will be monotonically decreasing? That's the real question, right? So because I've got to satisfy, I want f to decrease, but I also need to satisfy the constraints. And I can always make f go down by violating the constraints, right? So like that's not good. So I actually need to do something a little different there. And so you want something to monotonically decrease, but what's the something? So that is a good question. What would you do? Like, what's a good thing to look at? It turns out that doesn't quite work. Not the well, the Lagrangian itself, yeah, is not the thing you're looking at. There's some other things we'll talk. Did anyone have any other questions on this, or want me to try anything weird before we go into that? Yeah. That's going to be annoying though. I don't have a nice way of dumping it out. Yeah, you can do it. You have the code. But yeah, so basically I'm forcing the eigenvalues to have the right signs, you know. Okay, cool. So let's keep trucking. Sorry, we lost a few minutes at the beginning today because of the annoying stuff. So okay, cool. So basic message is in this example, like we did this regularization, but we still overshoot, which is bad. So we still need to figure out how to do a line search on these kind of problems. And this isn't too hard. We just need to kind of like be a little smart about it. So let's do that real quick. Yeah.
It's not required that we use the same beta.
Nope. Yeah, and I mean, this is just the simplest thing, right?
Yeah.
In general, like you wouldn't do it this way because computing the eigenvalues is quite expensive. There's better, cheaper kind of things to do. Another thing to mention about this is there's specific linear solvers for KKT systems that are like special case to that because they show up so much in optimization. So the really common ones are called LDL factorizations. It's sort of like Cholesky, but it pulls out a diagonal as well as the lower the L. So Cholesky's LL transpose. I don't know. Maybe this is too off the topic. Basically, there's specialized linear system solvers for those kinds of KKT systems, and they can detect these kind of eigenvalue issues like in the inner loop as they go, and then kind of fix them in an online fashion so it doesn't involve like all this extra compute cost. Okay, so let's talk about line searches one more time. Okay, so the big story here is something called a merit function. So this is kind of what we were just getting at, where I can't just look at the objective function because then I would violate the constraints. It turns out also the Lagrangian itself isn't quite the right thing. And instead, what we need is some like surrogate function for measuring like progress towards a stationary point or an optimum. And we're going to call that thing a merit function. And basically, we get to make this up. We just have to pick one that's reasonable. And that's the thing we're going to use in the line search. So the way into this is we're going to just talk about, way back to the beginning, we talked about root finding. So we're just trying to find a zero of some function, some vector function in general. It's not a min, it's not a max, it's whatever, it's just a root, right? So then the question is, how do we do a line search on a root finding problem? Which we kind of never did, right? We went right to minimizing, and then it was obvious what to use for this. It's the objective function. But, okay, so here's the problem, right? I'm doing find x star such that C of x star equals 0, right? That's root finding. Okay, so thoughts, what should I do? If I want to make sure I don't overshoot, right? I want to do a line search on this. What would you do? So the intuition is I want something that's going to like be hopefully monotonically decreasing, right? And that's how I'm going to decide if I keep the step or not, if I'm making progress towards a root. So what do we think? What's like a reasonable thing to do here? So I'm going to write some stuff down. Then I'm going to ask somebody to think about it and tell me, yeah, just go for it. There's no wrong answers. It can be basically anything. Well, I mean, this is it, right? There's no KKT. It's just this. Like I have some random function, C of X, and I'm trying to find a root, a 0 of C of X. So think about it like I'm trying to find an equilibrium point of a dynamics, model or something like this, right? I want to balance the robot on one leg, and I'm looking for the pose where it balances, right? So that would be kind of a C of X equals 0 situation. So any thoughts? We need so a scalar function we call a merit function. And I guess we'll call this P of X that measures distance to a solution. Okay. There's one like really obvious one. So, well, okay, there's no gradients here either, right? Like this is just a root finding problem. Like all these are reasonable things in particular contexts. Okay, so right here, I'm trying to drive this thing to 0. So anything that's not 0 is worse. So just take the norm of C, right? Like, and I want to drive C to 0. Okay, norm of C should be 0. So like that's a very reasonable one, right? That sort of makes sense. So like that's one of the standard choices. So I can choose P of X is, say, squared, 2 norm kind of thing, C transpose C. You could also just use literally any norm. So another very common one is a 1 norm, because it's cheap to compute. So these are for general root finding problems, right? Or just trying to drive that thing to 0. So obviously, all the optimization stuff we've talked about is doing root finding at the end of the day. So I can do either of these, but it turns out there's a little bit more structure in those optimization problems that you can leverage to maybe make up nicer ones or cheaper ones to evaluate. So basically, you just do this, and now you just do Armijo that we've already done on this merit function instead of like an objective function. So to be super clear, we got our Armijo thing. So we've got like alpha equals 1, sorry, like a full step. And then we're gonna kind of evaluate this condition while P at the new X is bigger than P at the old X plus this kind of linearized expected decrease thing. So grad P times delta X. And then we've got our tolerance in here, right? And then this guy's the step length. Okay, so while we're doing that, we're just chopping this down. I think, we used C before, but I think I used that for the constraint, so that's not good. So we'll kind of pick a different letter. You do this, right? Chop it in half, say, until it works. And then after that, we sort of take the step once that condition's satisfied. Just like before, right? The only difference is we're using this merit function thing. Okay, so that's root finding. And as we already talked about, right, we can totally apply this to, say, a KKT residual, right? So KKT residual, like I'm trying to drive that thing to 0. It's a root finding problem on the KKT conditions. I can just do this to the KKT conditions in principle, right? But maybe there's some other choices that are better. And we'll talk about that real quick. So, for instance, right, if we've got something like this, minimize f of x, and we've got inequalities, say C of x greater than or equal to 0, and equalities d of x equals 0, stuff like this, right? I've got my Lagrangian, which we already know about. And here, right, like I kind of alluded to, we're going to have 2 multipliers, one for the equalities and one for the inequalities. So we got f of x, and we'll make lambda be the inequality one, and mu be the equality one. Okay, so lots of options for merit functions here. So the first kind of sort of obvious one would be to use the KKT residual. So we're basically going to take, we got that lambda thing, we got this L, we're computing the KKT residual anyway inside our Newton thing. So we can just take a norm of that and use that. That's one option. So we got P of x lambda mu, and we'll make it, say, squared 2 norm. So like 1/2. We'll call this R KKT, which is literally grad L respect to x, grad L respect to lambda, blah, blah, blah. You get the idea. X lambda mu. And we're going to say take this and square it. This thing is KKT residual. And in our case, right, if it's kind of all of this stuff, it's going to be grad with respect to x of our Lagrangian, which we wrote up there, and then it's going to be the constraint violations. So for you got to be slightly careful, right, because it's you only want to take the sort of negative part of the constraint violations, right? So this would be this guy. Oops. Yeah, there we go. And then the equality stuff, right? Okay, so that's sort of what would show up in there. So that's one option. Why might I not want to do that? Any thoughts? This is like the default. It's exactly what we just talked about in the root finding case. It definitely works. You can do this. Why? What's like maybe not desirable about this one? Anyone have any thoughts? Yeah.
Large disparity in values, like between x and the lambda. Harder in one direction or something.
Yeah, maybe. So the big one is actually kind of dumber than that. It's just that it's so in the Armijo rule, we need to have grad p as well. So evaluating this guy is fine. Like I have to do it anyway, but evaluating this guy's gradient is maybe annoying. You have all the stuff to do it, right? If you're doing full Newton, you've got all of that, but it's actually pretty expensive to evaluate this thing's gradient. So because this is all kind of fudgy anyway, and I've got this like tolerance on it and whatever, it's not worth spending a lot of compute to compute that term, right? So that's kind of the so in general, maybe we want to find something that's a little cheaper to deal with computationally. So there's some other choices. Did you have something? Yeah. Did I screw this up? So I want it to be, so if it's min, yeah, I think you're right. I'm switching signs in my notes as I go because which is not ideal because I had C of X written the other way last year and I forgot to update these ones. So there's a little bit of mental gymnastics going on that I'm obviously screwing up as we go. So this should be a min, that's right. Yeah. The negative part is the bad part. That's what I want. Okay, cool. Okay, so other choice you can make is, and this one is extremely common in large scale nonlinear programming solvers. So I can take, let's say we'll write it, this other p, blah, 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 is, so we can take the objective function, which is kind of what we would have done if it was unconstrained, and then we could just add a penalty term on the constraints. So in particular, I'll put some scalar weight on there, and I'll just take the norm of the constraint violations. So in this case, right, I do like min, I clip the inequalities, right, just like we did up there, and then just, all the violations on the equalities and take any norm you want, but it turns out the one norm is particularly nice for this because it's cheap, obviously, right? And then it turns out the gradient of that is also cheap to evaluate, and I already have all the stuff I need sitting around. So this is some scalar weight. And then, as before, any norm works here. Okay, cool. Questions about that? So this second one with like the one norm penalty is actually uber common for what it's worth because it's cheap and easy to do. Okay, so now we're going to try this on some stuff. So let's see what we got here. Okay, cool. Same problem again. And we're gonna start at the bottom. And remember before we did this, we took like a really big step, kind of went way off the constraint toward, which makes sense, right? Because like what we're ultimately doing in those KKT conditions, we're linearizing the constraint. So basically going along the tangent line at the bottom, and we're minimizing along that linearized constraint. And we know where the minimizer is, right? It's in the middle of the bowl there. So like if I were to minimize along that tangent line, that's exactly where I'd go. So this makes complete sense. It's just that in this particular case, I've like shot way off the constraint, and that's probably bad, right? This is a fairly benign problem, so it still kind of works out. But in general, something like that could hose you and you would be in bad shape. Okay, so But yeah, thankfully, I think this thing still makes it, where we want to go, and maybe, a few iterations, cool. Okay, so let's try some of these things we talked about. So here's this one is the kind of KKT residual squared two norm thing. So here's our like KKT residual thing, right? And, all that. And I just take, its dot product with itself, blah, 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 all good. And then this is grad P. And as you can see, this is kind of annoying to compute, right? I have to compute a bunch of the Hessian stuff. I might already have this laying around, which is cool, but the problem with this is it's actually evaluated sort of, it's more expensive, kind of end of story. So that's that. And you'll see, okay, so we have this guy, and then this is the other one. And you can see that this one's substantially cheaper to deal with, right? I don't have to compute like Hessian-y stuff here. Okay, so let's try this one first. We're going to kind of do the same exact thing. I think I need to go start this over again up here. So we're going to start back at the bottom here. And we're going to run it with the Armijo rule on this merit function. And we're going to start with the just KKT residual. So that's all we're doing. So we're going to make sure the KKT residual is going down. So you can see we took a way smaller step, because now this thing's saying, oh, well, if I step way out there, I'm going to start violating a constraint a lot, and that's bad. Cool. So this thing, take another step, right? So now we're kind of going along this tangent line, right? So this is all kind of nice, and you can see we're relatively closely tracking the constraint, and now we're kind of, honed in the right spot, and we get like kind of the 4 or 5 iteration Newton behavior that we like. That looks good. Okay, let's try the other one. So this guy, exact same deal. So this is, one norm of the constraint added onto the objective with this little penalty weight row. I'm going to set that arbitrarily to 1 right here. We'll give this a try. Same kind of deal. I got to restart up here, set this thing back to where we started. Okay, so let's see what that one does. This is super annoying. Sometimes this does like weird, it's a weird bug. Okay, cool. Let's try this. So really similar behavior, does the obvious thing, right? It's basically weighting constraint violation in that check in the Armijo rule, so it's not going to let me step too far, and it looks pretty much exactly the same. And now, 4 or 5 iterations, we're where we want to go. Cool. Life seems good. Now here's a question. How do I decide what this row should be? It's kind of an arbitrary tuning parameter. So in general, it can be tricky to decide on a good row, and it kind of depends on the scale of your problem. And I'm going to point out a bad thing that can happen. So let me set this to like 10 now, and we're going to do this exact same thing again. And what do you think is going to happen if I jack that thing up too high? Have any thoughts? So yeah, basically this thing's penalizing constraint violation. So if I really jack up that penalty on violating the constraint in my line search, means and my constraint's really curved, means I'm going to end up taking uber tiny steps in like along that tangent line to the constraint, and it won't let me take big enough steps. That's kind of the possible bad thing that can happen. So let's check that out and see. In fact, that is, so yeah, you can see I took like almost no step, and if I kind of like keep iterating this, it's going to take me forever to get to the optimum, because it's forcing me to hug the constraint like too tightly, essentially. Okay. So this thing has a name. This is called the Maratos effect. You can look it up in some books. And basically, it's the fact that for line search methods, when you have nonlinear equality constraints, where there's curvature in the constraint that's getting dropped out in the linearization, if you kind of weight in your line search constraint violation too heavily, you can basically end up backtracking way too far and essentially making no progress. This is bad. So, kind of one of the things you got to worry about is tuning this penalty weight in here appropriately. And there's methods that will kind of auto tune this for you that you can find in the literature. But even that can actually not work super well. And so in general, the way around this is with a set of tricks known as second order corrections. So the gist is you take your step, and then instead of just like backtracking and looking at those Armijo conditions, you actually evaluate the constraint function at the new step and do like one more back solve, if you like. So think about it as like a cheap lazy Newton step where you don't update the KKT matrix or the factorization. You just evaluate the right-hand side C of X violation at the new step. And then you plug it back in and solve that linear system one more time, which it turns out is cheap. And that kind of will like pop you back towards the constraint at the new the new step location. So that turns out that second order correction fixes this problem because it gets you sort of, it turns out if you Taylor expand that, it gets you constraint satisfaction that's good to second order in the Taylor expansion of C of X, which captures the curvature. So it helps us a lot. FYI, you can look it up. So Maratos effect, line searches can do bad things in general. Life is hard, right? I keep telling you about, we're going to fix a problem and then there's a new problem, right? So I think this is where we're going to stop though, just so you know, right, that this is a thing out there. Okay. Yeah.
The Armijo.
Yeah.
Like gradient of numeric function. Like why can't we just go until we decrease?
Yeah, so this is kind of the same story we had before with the, like, you can create perverse examples where if you basically overshoot and zigzag forever, or zigzag for really, really long. So if you make it less than or equal to, you can like create functions where if I start here, I'll end up bouncing over here and then bounce back and I'll zigzag and not make any progress. If you make it strictly less than, you might get a little better than that, but you can still get a situation where you end up doing this for a really long time. So the gradient condition there is designed to avoid that zigzagging phenomenon. And like there's fancier versions of these line search ideas, namely the Wolf conditions that you can look up to kind of, up the ante and use the second order term in there. But that's kind of the thing they're trying to avoid is excessive zigzagging. Cool. Okay. Yeah.
Computing a gradient of the net function anyway. Could rho be a function of that?
I mean, sure, I guess so. And that's sort of now getting to these fancier line searches. So probably the thing to look up there would be a so-called cubic line search. And what that's doing is I know X, I know grad X, grad f of X here. And I now know f at X plus delta X, right? So I know 3 things. If I evaluate the gradient here as well, now I know 4 things. I can fit a cubic. And then I can actually exactly minimize the cubic. I can do all kinds of fancy things. The fanciest thing you can do is a so-called exact line search where you literally solve a new 1D optimization problem in alpha, which is not very practical because it's expensive to do, blah, blah, blah. But there's lots and lots of fancier things you can do that involve like using multiple, evaluations of the function and its derivative to like, do some more fancy interpolation and more fancy minimizing along the step length. Cool. Okay. Yeah.
Are there sort of line searches generally for me or like invariant searches that
this is, I think, one of these like no free lunch situations where like on a given problem, like you might find one or the other's better. And obviously there's a bunch of tuning parameters and all these things, right? So I'd say in general, like there's no kind of like really hard conclusions to draw. There's all kinds of things out there. Yeah. I think the filter line search thing is an IP opt, and there it really helps. It turns out doing interior point methods on non-convex problems is really, really gnarly. And you can get into really bad situations where you get stuck at an infeasible point, like you're stuck off the constraint manifold. And those things can help in kind of some of those weirder situations. It turns out like nonlinear programming is super hard. Like there's all kinds of crazy things that happen, and trying to make a general purpose nonlinear solver like IPOP there's tons of tricks in there. It has all kinds of really crazy stuff. So it's in general really hard to do that well. Life is hard. All right, cool guys. Oh, Maratos. I'll throw this up on the Piazza if you want after, so I'll send you some references. The place to go for more of this stuff, by the way, 2 books I highly recommend. One is Nosidal and Wright, Numerical Optimization. So that's the book with all of the like practical like pseudocode, how to implement all these algorithms kind of stuff. Has a section on the Maratos effect, has a whole thing on line searches and all this good stuff. So that's like where to go for pseudocode to actually like implement an algorithm. And then more for like kind of the theory of convex optimization type stuff, I highly recommend the Boyd and Vandenberg book, Convex Optimization. So that's got all this stuff about like the duality stuff, like that's all in there. Okay, with that, we are done with our optimization crash course. I think know what we need to know, hopefully, for the rest of our class for our purposes of like doing some optimal control. There's lots more to this. It's a whole field, right? So, but hopefully you guys know enough now, and it's been fun. Okay, so with that, we're going to do, as I promised, a little palate cleanser and try to, clear the air and get into some like control stuff. So this is just for fun. It's not like there will be no quiz. There will be no test. It's just for I don't know. This is my take on the last 100 years of control theory and like what the field looks like, just to give you kind of like a, I don't know, 10,000-foot view of the field and like what's cool and what people have done and all that good stuff. Okay, a brief history of control. Here we go. Please speak up, asking questions, interrupt. This is very like rough. So in the beginning, you don't know what this thing is? The Brachistochrome problem. Who's ever heard of this before? A bunch of you. Where'd you hear about this? Last year, no one knew what this was in this class. Like, where did you guys hear about this? Where? From where, though? Is this like a... Okay, yeah. Veritasium or one of these like, yeah, okay. That's interesting. Yeah, there must have been some YouTube video that talked about this because last year, no one knew what this was. So this is kind of fascinating to me, like what gets around on the YouTubes. Anyway, so yeah, someone tell me what this problem is then, if you've all seen the YouTube video. It's probably better than me. So the problem was so it's a ball rolling down a ramp, and you're trying to find the shape of the ramp that gets the ball to the finish line the fastest, just passively under gravity. So this is kind of a fun historical thing. This was posed as a challenge in whatever, version of journals they had back in like 1690. And it was posed by one of the Bernoullis. It turns out everyone's heard of Bernoulli, probably from like Bernoulli's principle from like, wings for airplanes and stuff like this. Turns out there were a ton of Bernoullis. There were like originally two brothers, and then they had some sons. So whenever you hear Bernoulli, you have no idea who it was. It could have been like 4 or 5 different people over like, decades back then. So they posed this problem in this journal. And then it was solved independently by 3 of like the big names from, mathematicians of that era. So Newton solved it, Leibniz of, calculus fame solved it, and L'Hopital of L'Hopital's rule solved it. So all 3 of them like submitted solutions and got the answer. The fun thing though is that one of those, so they all got like different solutions, right? And one of them though, and Newton's one, actually sort of developed an entire new branch of mathematics that turned out to be pretty important and is still like kind of a thing today. And it forms the basis of modern optimal control theory. So in particular, like this is basically how Newton solved it in modern notation. And it's this thing called calculus of variations. Who's heard of that? From the same YouTube video? Maybe. No, not from the YouTube video. Okay, cool. So this is the solution. It turns out, fun fact, the solution to this, the shape of the ramp, is something called a cycloid, which is if you like roll a wheel and like stick a marker on like the rim of the wheel, that red curve that it traces out, that is the solution. Kind of random. You wouldn't have like probably figured that out without doing some of this stuff. So this is the math. This is what it looks like. But this calculus of variations thing it runs really deep. Okay, so Newton like came up with it to do this one problem, but then we've been using it for like 300 years or whatever since then. The gist is this should now look sort of familiar, or maybe. So what calculus of variations is all about, it's an optimization thing, but specifically all the optimization we've been doing is optimizing with respect to some vector x, right? A finite dimensional vector x. What calculus of variations is about is optimizing a function. So rather than x being, say, like a 10-dimensional vector, x is x of t, a continuous function of time, right? So it's like this kind of, you can think about it as like an infinite dimensional version of the stuff we've been doing. We're not going to do it because we're just going to discretize everything and do it in finite land where things are kind of nice, but you should know about this. It's a thing. That's kind of the pretty standard setup. If anyone's taken a mechanics course, that looks like, how you get the Euler-Lagrange equations, right? That is an instance of this stuff. It shows up, it turns out, in lots of applications, not just optimal control. So it shows up in statics. Does anyone know what that hanging chain problem is called? That was another kind of one of these like, I don't know, like 18th century things that physicists and mathematicians thought about a lot. It's called a catenary problem. Yeah, so it's the shape of a rope or a chain hanging under gravity. Do you know how you solve that one with these kind of tools? How is that a trajectory optimization problem? That's a fun question. So it turns out you're solving for a continuous curve, like the shape of the chain, right? So you can parameterize that as a function of like length along, like path length along the chain. Looks just like time for a trajectory optimization problem. And what do you think you minimize? Yeah, potential energy. Yeah, so you basically write down the energy of this thing under just gravity, right? It's like mgh. And then you can like minimize that, right? And you'll get out this shape. So that's statics. It turns out Fermat's principle in optics is another version of this, right? So you're trying to basically find like minimum length paths for rays of light through different media, right? With different effectively like speeds. Classical mechanics, this shows up as Hamilton's principle, which is how you get the Euler-Lagrange equations, which are the manipulator equations from robotics. So that's kind of one other. It turns out these things show up a ton in finite element methods, both in like solid mechanics and fluid mechanics. And there they call this like the weak form or weak formulation, if you've ever heard of that. Similar deal. In general relativity, this is how you do it. It's very similar stuff. It's called the Einstein-Hilbert action. And then in quantum mechanics, if you've ever heard of Feynman path integrals, there's a way to do quantum mechanics with this stuff. The way you might have heard of that, by the way, is it's circled back into control from quantum mechanics. There's this thing called the Feynman-Kac lemma that, so in quantum mechanics, this is stochastic. And it turns out, if anyone's heard of MPPI, model predictive path integral control, it's called the Feynman path integral. So it turns out MPPI is taking this thing, got into quantum mechanics. They developed a stochastic version of it for quantum mechanics. And then it went full circle and came back to control in the form of model predictive path integral control, where it's sort of, trying to do stochastic MPC with this kind of stuff with sampling. So same stuff, kind of interesting. It shows up all over the place. Okay, fun. So this is like really ancient but still kind of comes back once in a while. It's good to know about. Okay, so feedback. Does anyone know what this thing is? No YouTube video on this one?
In control.
Yeah. What did he?
Very first episode talks about.
Oh, really? Okay, so what is it?
The governor.
Yeah, this is the centrifugal steam, the governor on a steam engine, right? So this was invented a really long time ago by Huygens, another famous name, I think 1788. This is me doing some Wikipedia just to get the dates right. So anyone tell me what this thing does? It's kind of cool. Yeah. So if you have a steam engine, there's a throttle, right, which is literally this like valve that opens and closes, right, to govern, the temperature and whatever of the steam engine. And if you want to operate the steam engine, if you want the output shaft to basically spin at a constant rate, right, independent of the load. So you can imagine you're pumping water or whatever it is, right? So you want the shaft to keep spinning at the same rate as the load changes, right? So if I have more load on there, it's going to slow down, right? And if the load gets lighter, it's going to speed up. So how do I counteract that to keep it spinning at the same speed? So what this thing does is it's spinning around and it has these two masses on levers that go out and in, right? So as it spins faster, centrifugal force lifts those masses up and it closes the valve a little bit, which makes the throttle go down. And likewise, if it spins slower, they drop and it opens the valve back up. So this is super clever. It was invented again 1788, and then beginning in a few decades after that, this thing was used. This was a major piece of the Industrial Revolution in like the 18th, 19th centuries, and most famously, probably this was James Watt used this on the first steam engines, right? And that was that's the 1788 one. Okay, so this is kind of a big deal, but back then, no one knew how this actually worked, and there was no formalized mathematics for kind of analyzing these things. So I want to know who did the first kind of mathematical analysis of this. This is fun. So Maxwell, of Maxwell's equations from electricity and magnetism. So a huge name in physics, I think underappreciated, that he also could I think plausibly be called the founder of control theory. So he published a paper in 1868 in like the Transactions of the Royal Society that was the first rigorous mathematical analysis of this, where he looked at like closed loop stability and all this kind of stuff. And it's up on archive.org. And I actually highly recommend checking it out. It's like surprisingly readable. It looks like a modern paper. And it's basically the math in it is like frequency domain, kind of analysis with Laplace transforms. It basically reads like something that would have been in your undergrad SISO controls course. You can totally read it and understand it. And it's that old. It's kind of wild. It looks like stuff, that you'd be familiar with from that kind of class. Cool. So yeah, basically that Maxwell paper used a bunch of like concepts from modern, when I say modern, 20th century classical feedback, right? It's got linearization, stability analysis for small errors kind of stuff. It's using Laplace transforms, all the good stuff. It's kind of fun to check it out. So that's 1868, right? So that's kind of, I would argue that's kind of the real origin of like the field in some sense. And that kind of grew from there into what we call like classical control. So if you've taken any kind of undergrad class where you've done like Laplace, root locus, Bode, all that stuff, that basically all comes from this period. So right in the basically early first half of the 20th century, there was like a big explosion of work in that kind of vein. And you got things like the first autopilots for airplanes, really shortly after airplanes were invented, it turns out. First, you got automatic steering systems, basically autopilots for ships around this time. So first automated steering system for ships is like 1911. First autopilot for an airplane was 1914 by a guy named Sperry, who that's a big name, right? They had an avionics company for many years. And this is where still at that point, this was like Wild West stuff where people are just trying stuff. Basically, they were doing PID back then, but there was not a real formal theory. The theory started getting developed in the 1920s, and that's where all these names you've heard of, like Bode, Nyquist, et cetera, kind of came up. Mostly that was happening in electrical engineering. So they were working on things like vacuum tube amplifiers, radios, power systems, things like that. And that's where all those classic frequency domain tools based on Laplace transforms and stuff like that happened, mostly in the 20s. Yeah, so like phase and gain margin, root locus, all that good stuff, mostly 20s. The next major development was World War II. There was a lot of stuff, you can imagine. And in particular, there was a lot of work on like fire control systems for pointing anti-aircraft guns, a bunch of stuff for torpedoes and missiles. And one of the big leaps forward was the V2 rocket, which was the first rocket to reach space. And, rockets are unstable systems, right? It's a big inverted pendulum. So getting stuff like this to work requires feedback control. Like rockets do not work without stabilizing feedback. Okay, so that's like gets us up to like, say, just after World War II, maybe. And that's where the next sort of big leap happens. I said 60, it's maybe late 50s. But this is where we talk about the modern era of control. And what made all of this happen was computers. So basically we went from like this CISO, Nyquist Bode drawing weird plots on log paper and stuff like this, right? And really have to analytically come up with these things and then build them out of individual circuits like vacuum tubes or best case op amps to being able to like solve matrix equations on a computer in real time. So anyone know what this picture is? It's another good one. No space nerds in here. Come on. This is the Apollo guidance computer. So this was like a really, really huge deal. This was actually developed at MIT in what was called at the time the Instrumentation Lab, which is now Draper Labs. So they figured this all out. Let's see. So the big names here, one of the biggest names is Rudolf Kalman, Rudy Kalman of the Kalman filter. But it turns out he did more than the Kalman filter. He actually developed the entire like kind of state space idea, right? So he took us from, this weird frequency domain Bode plot stuff into, no, we're going to write down differential equations and, we're going to have, matrix sort of differential equations for this stuff and state space where we look at, positions and velocities and whatever. That whole idea really came out of Kalman, and then kind of attacking these problems with all the tools of both, theoretical tools and numerical tools of modern linear algebra on computers. So that was really Kalman's thing. He brought kind of modern linear algebra and matrix math into control, which kind of wasn't really a thing before that. And it only really became possible because we had computers to do that kind of math, right? You wouldn't do that by hand. Interestingly, there was a lot of resistance to this at the time, and Kalman couldn't get his original Kalman filter paper published. Or he was like working in electrical engineering. The paper got rejected a bunch of times, and he could never get it published in like IEEE or whatever. So he ended up publishing it in an ASME journal in mechanical engineering. And again, it took like a really long time. One of the really cool anecdotes. So he publishes the original Kalman filter paper. Beautiful paper, by the way. You should totally read it. It's all like geometric. It's all about like projections and all this kind of stuff. It's like super, it's always really good to go back to the original like masters on this stuff. Highly recommend, because like if you read this stuff in a textbook now, it's all like Riccati equations, there's a bunch of algebra, and there's like no insight. The original Kalman paper, it's like he had to wrestle with this stuff, right? Like he had to actually come up with it to begin with. So there's a level of like intuition, in there that you don't get in many other places. And specifically, the derivation of it is all like geometric, involving like projections and stuff like this. It's really cool. Highly recommend. There's one textbook that does it that way that I know of also, which is pretty nice. That's Kyleth Linear Estimation. That's got the pretty geometric derivation as well, but it's not common, which is sad. Okay, so Kalman puts this paper out. The really fun, as a space nerd, kind of anecdote about this is that I think that paper dropped in like 63 or 64, something like this. And this was like right at the height of the Apollo program when they were trying to figure out how to fly to the moon, right? When all the engineering work was going to get done. And that paper was like a theory paper, right? It was linear systems, blah, blah, blah. So this guy named Schmidt, who was working, I think, at NASA Ames at that time on guidance navigation for the Apollo missions to fly to the moon, they were trying to figure out how to do that. And he went home for the weekend with like a printout of the Kalman paper, read it over the weekend, and like over the weekend invented the extended Kalman filter, i.e., linearizing a nonlinear system and iteratively and applying the linear Kalman filter equations to it, which is, by the way, if you look it up, it's also called the Kalman-Schmidt filter. So that's Schmidt, the other guy. He was a NASA engineer. So he invented both the EKF and the square root Kalman filter, which is widely used in embedded systems because it has better numerics than the original one. He invented both of those over the weekend and showed up on Monday with the answer. And then they like implemented it on that thing and flew to the moon. Pretty awesome. So that's like kind of the US side of the story. There was, in parallel with this, there was obviously, the Russians were also building rockets and trying to, do stuff in space. And so they had very similar problems. So there's also some big names there, namely Lev Pontryagin, right? Pontryagin minimum or maximum principle. So he developed basically the first order necessary conditions for an optimal control problem in continuous time, which are coming straight out of that calculus of variation stuff. So that was his big contribution. That was published in the late 50s. And then the other big name from this period is Bellman, Richard Bellman, founder of, so that's, dynamic programming, all happened in the same time. So like within about 10-year span, you had Pontryagin, Bellman, Kalman, like all of it happened in like a really short span of time. And all of it really was just because there were computers now and people could actually solve, like in Kalman's case, right, solve like big matrix equations. Pontryagin case, they were solving 2-point boundary value problems with numerical ODE solvers that now are practical. And in Bellman's case, they were doing sort of grid world dynamic programming stuff, but you had to have computers do all of this, right? So kind of wild how much of that stuff happened in like such a short period. Okay, so that's kind of 60s where we're at, right? Space race stuff, computers. Sort of the next kind of thread I would argue is like there's now I'm just going to kind of highlight several interesting threads, right? So then another one that kind of cropped up, it actually was there, kind of all along, but kind of really got big after World War II is adaptive control. So this is kind of this idea that like, we don't really know what the dynamics are ever. There's always uncertainty in there of varying degrees. And how do you, you can think about it as adaptation online, right? You can think about it as parameter tuning, right? If you have a linear controller, you want to tune the gains online in response to what's going on in the system. So this question was kind of there going way back. And it really started to see real attention starting in the 50s with high performance aircraft. Anyone know what that thing is? The top. So it's the X-15. This thing is, I think, still the fastest ever like winged aircraft. It actually flew into space. So a bunch of the guys who flew this got astronaut wings, but it's a rocket plane, has wings, flew crazy fast. But they were testing these kind of crazy adaptive control systems on this. And where this shows up on these airplanes is that they're flying through very different flight regimes. So Mach number, altitude, all this stuff. And the idea is that you would like the autopilot, the control system, to retune the gains in these different flight regimes, right? That's kind of the idea. Unfortunately, so they were just doing this stuff. So literally what they were doing is running gradient descent. In modern terms, they were straight up running gradient descent on the policy parameters in the loop on the airplane with a dude sitting inside of it. Absolutely terrifying. So this is like the cowboy era, right, of this kind of stuff. They had no stability results whatsoever. Arguably, this is what we're doing now all over again with like online RL, right? Like not a lot has changed. The things have just gotten bigger. So there it was a linear feedback policy where they were doing online gain tuning, but they were literally taking gradient descent steps on some, performance metric, with the thetas, the control parameters. And it turns out bad things can happen. Someone died, they crashed an airplane because this thing took a gradient step that drove the closed loop unstable and it crashed. So not great. But then, yeah, people started to like look at this and try to formalize it and develop a, kind of convergence and stability theory to make sure things like that didn't happen. And let's see, what else? Yeah, so guarantees for that stuff. And then, yeah, kind of coming into the modern era, right? We've all seen this stuff, but I would say you can draw a pretty clear straight line through from like that stuff in the 50s, 60s into like this kind of stuff where we're doing online RL on modern robots. The line is surprisingly, kind of continuous and direct there. Like people in the control community, like literally adaptive control people in the 70s and 80s were using neural network policies, doing backprop. Like backprop has been reinvented 3 or 4 times independently. Some of the earliest derivations of the backprop method were by control theorists in the 60s, like Art Bryson at Stanford invented backprop. It was reinvented multiple times. But basically, control people have been doing that stuff all along, right? Like Chris Atkinson has some funny anecdotes about like he was in grad school in the 80s and neural nets were really hot, right? And everyone was doing like reinforcement learning with neural networks. So it's all kind of been there for a long time. And there's a long heritage and legacy for all these things. So I encourage you to go back to the roots and like think about like people have been doing this stuff a long time, and it's not like the stuff that people are doing now has roots that go back, at least 50 years, right? Okay, so that's adaptive control. Oh yeah, this is awesome. You should know about this. So has anyone seen this paper before? A couple of people. So this is a really famous paper by this guy, John Doyle, who's still around. He's a professor at Caltech, really famous control theorist. And he's in some sense like the father of the next kind of era of control, I would say, robust control. So robust control is all about, so we talked about adaptive control is like there's errors in the model and I'm going to try to fix those errors online with data, right? I'm going to try to retune, update things given the data and try to do better. And are we out of time? Just about now. Well, I'll finish this up. So this is his first paper that kind of spawned the field. And I think he was like a brand new grad student or something. And basically proved that if you have epsilon perturbations in your dynamics model for a linear system, this is a LQG. So this is with a state estimator. This is LQR and a Kalman filter hooked together. But he showed a couple of counterexamples in here where for tiny, tiny epsilon perturbations in like your ABC matrices, the system goes unstable. So then this spawned this whole field of robust control where you're trying to not adapt, but you're trying to bound the errors that you think could happen and design control policies that will be stable in spite of a bunch of those errors. Anyone know what the modern version of this in RL is called? How do we do robust control now? It's domain randomization. That's like the modern kind of version of this stuff in neural network policies. Okay, we got to get finished up here, but yeah, MPC, we're going to do a lot of, this sort of started in the 70s in chemical process engineering, still a big thread. There's a huge group here in Chemi that does this stuff still. But then started to get into robotics starting in the like 80s, 90s as the computers got faster. This is where you solve an optimal control problem online at real-time rates. What else we got? Manipulator stuff. Yeah, we should probably finish up. Legged robots, cool. Lots of history there too. Raybert and Honda in Japan doing cool stuff. Very, very different control techniques. And then the modern stuff is, MPC is awesome. And I think we got to call it there because we're out of time. But thank you guys.